All right, everybody, welcome to today's Astroparticle seminar. I'm very happy to have today Rafael Alves Batista as our speaker from Radboud University at Nijmegen. Rafael did his PhD at the University of Hamburg in Germany. He was in a postdoc at Oxford, then a postdoc at Sao Paulo in Brazil. And now he's a postdoc at Nijmegen University, the IMAPP, the Institute for Mathematics, Astrophysics, and Particle Physics in the Netherlands. Rafael has worked and works on several aspects of ultra-high energy astroparticle physics. It includes the detection of point sources of cosmic rays, of ultra-high energy cosmic rays in cosmic ray maps, the effect of extragalactic magnetic fields on ultra-high energy particle propagation, learning about intergalactic magnetic fields from the observation of ultra-high energy cosmic rays, and cosmologic neutrinos that come from the interactions of ultra-high energy cosmic rays on the photon backgrounds. He's also one of the developers of CR-Propa, one of the leading codes to calculate the propagation of ultra-high energy cosmic rays. And he's a member of several experimental collaborations like Auger, Grant, and CTA. He also has, this is something I like, a broader interest in other topics like how resilient extraterrestrial life could be to global sterilization events like supernova and GRBs. And also has a keen interest in the connection between science and philosophy. And he has recently been the editor of a book titled Fine-Tuning in the Physical Universe. It has contributions from different people studying fine-tuning in different aspects of physics. Today, he won't talk about that, I believe, but he will talk about propagation of astroparticles, multi-messenger view. And with that, I leave you, Rafael. Thank you.
Okay, thank you very much for this nice introduction, Mauricio, and for the invitation to speak to the group here. It's a pleasure to be here, at least virtually. So today I'm going to talk about the propagation of astroparticles in general, a multi-messenger view. And apparently I'm going to talk about different topics, but it's not. It's all about the propagation of particles and how they are connected. But because I'm going to talk about different particles like cosmic rays and gamma rays, it's going to be to feel like two different talks, but they are not. They are connected, as I'm going to argue in the end. Okay, so this is the structure of the talk. So in the first part, I'm going to focus mostly on the propagation of ultra-high energy cosmic rays and cosmogenic particles like neutrinos and photons coming from ultra-high energy cosmic rays. And in the second part, I'm going to focus more on the propagation of gamma rays and how we can probe intergalactic magnetic fields with gamma rays. And I'm going to make a stop in between these two parts because it's a natural point for you to ask questions in case you have some questions. Okay, so the first part is the propagation of ultra-high energy cosmic rays. I like to motivate this kind of talk by showing this type of plot, which shows the ultra-high energy cosmic ray flux at energies above 10 to the 9 GeV or so, together with the ice cube measurements of PV neutrinos, and the diffuse extragalactic background light measured by the Fermi-Lat satellite in this energy here. And if you draw a horizontal line more or less here, you can see that these are all connected through this line. So the flux of cosmic rays at 10 to the 9-ish GeV is roughly connected to the PV flux of neutrinos and the TeV flux of gamma rays. And because these fluxes are comparable, I should mention that this is E squared times the flux, actually. A natural question that one might ask is there a common origin for these fluxes? It's a very plausible question. There might be a common origin, there might not be a common origin, but we should investigate this particular issue, as I'm going to discuss later. But the point I'd like to make here is that this connection would probably come from cosmic rays, because the mechanism that produces these other particles, assuming that they have a common origin, would probably trace us back to the cosmic rays. And this plot, I'm sure you've seen several times. This is the usual cosmic ray spectrum. As you can see, it covers several orders of magnitude in energy. The low energy ones, they usually come from the sun, as you know. The intermediate, or they are actually low energy for someone who works at ultra high energy cosmic rays, but they are intermediate energy for those people who work on cosmic rays from the sun. So it depends on your point of view. But yeah, these cosmic rays here, they come mostly from galactic objects like supernovae, But we are more, at least I'm particularly interested in this very high energy part here, the ultra high energy part, which likely come from extragalactic objects. But as you can see, this overlap between the green and the orange shaded regions, it was on purpose because we don't really know where the galactic cosmic ray spectrum ends and where the extragalactic cosmic ray spectrum begins. And this transition from galactic to extragalactic sources, it's one of the main open issues in astroparticle physics today. So there is a transition. It probably happens at some given energy. We don't know at which energies. We believe that they are mostly extragalactic here and they are mostly galactic here, but it's not very clear what happens in between. And concerning the ultra high energy cosmic rays, which is essentially this part here, it's interesting to show, to understand the features of the cosmic ray spectrum. People like to compare the features of the cosmic ray spectrum with a lag for some reason. So this lag has some features. It usually has the knee. The knee, it's due to cosmic rays, likely cosmic ray protons being accelerated up to roughly this energy, 10 to the 15 electron volts, by galactic objects. There is also an ankle here at 5 times 10 to the 18 electron volts. And the ankle, it's not clear what causes it. Some people argue that it's due to the interaction of particles with background radiation fields. Some other people argue that the ankle might be due to a transition from the galactic to the extragalactic cosmic rays, or there are many other possible explanations. And here in between, people they saw a second knee here. I cannot see a second knee here. It's not anatomically possible for me, unless it's a broken leg, but there is a spectral exchange here around 10 to the 17 electron volts, which is usually attributed to a higher energy nuclei. Here it's for protons, here it's for the higher energy nuclei. So this would have the same kind of acceleration mechanism in the galaxy. Interestingly, if you look at the composition here in this particular region, that's what that kind of strengthens this interpretation of the knee being the first, the acceleration of protons, light particles in general, and the second knee being due to the acceleration of cosmic ray. Okay, so as I mentioned, the main questions in this field, one of them is the transition between the galactic and the extragalactic cosmic rays, but there are many other open issues. We don't know where the ultra high energy cosmic rays come from. We don't know exactly their composition, although we do have measurements, but we have measurements statistically speaking. We have distributions. We don't have an event by event measurement of the composition of the ultra high energy cosmic rays. And we don't know exactly how these cosmic rays are accelerated, nor by which kind of objects. Some of the problems that are interesting is, we see a flux suppression at 40 eV, but can this flux suppression, for example, be attributed to the famous Dreisen-Zapping Kuzmin Gdk cutoff due to the interaction of protons with the cosmic microwave background? That's an open issue today. It's not very clear, but the measurements of the composition of the cosmic rays, for example, tend to disfavor this interpretation of the Gdk. So nowadays we talk about this suppression at above 40 eV as being due to the maximum acceleration that ultra high energy cosmic ray sources can reach. And one of the first things that we need to understand, to really understand the ultra high energy cosmic rays, is how they propagate in the universe. So this is the picture that I always show when I talk about this. Neutral particles, they travel in a straight line, and charged particles, there are magnetic fields in the universe, so charged particles, like ultra high energy cosmic ray nuclei, they are deflected by these intervening magnetic fields, both extragalactic and galactic. And during their propagation, these ultra high energy cosmic rays, they can produce, for example, other secondary nuclei to nuclear decays or photo disintegration processes. And they can also interact with, for example, the CMB or other background photon fields like the extragalactic background light or the EBL, producing photons and neutrinos of cosmogenic origin, which is something I'm going to talk about today. Okay, passing this introduction, we are talking about particle propagation. So in order to really understand particle propagation, we need to bring together a few blocks, a few assembling blocks that allows us to really understand how this propagation takes place. The first one is the astrophysical inputs, which is we need to know which kind of injection is of cosmic ray particles or any kind of particle in general is emitted by the source. We need to know which type of particle we are talking about, or in the case of cosmic rays, what's the composition. We need to know how the sources are distributed in the universe and how they evolve cosmologically along the history of the universe. And then once we define our astrophysical inputs, we can perform the propagation. And then we have to understand how particles interact with each other, how particles are accelerated if this propagation occurs within a given small environment around an astrophysical object. But for intergalactic propagation, this is likely not relevant. We need to know all the relevant photon fields, as I mentioned, the CMB and the EBL, and background matter fields, depending on the environments that we are talking about, as well as the magnetic fields. And then we have the outputs of this, when we put all this together, and the output is usually the spectrum of particles, the composition of the particles, the arrival directions, and the arrival times. And then this is what we effectively confront with the observations by several experiments. And this recipe in general, it can be applied to any kind of particle that we are talking about. We just need to have these ingredients. We have to put them together, and knowing the physics of the interactions, we can get these outputs and compare with the observations. As I mentioned, one of these ingredients are the background radiation fields. We have here the CMB shown as a dotted black line. We have here these dashed lines is the cosmic radio background, which is not really relevant for most of the things I'm going to talk about today, except for the propagation of high energy photons. And here it's the EBL, or the extragalactic background light, which encompasses radiation, both the infrared and the optical parts of the spectrum. Yeah, I just said that. Okay, the other ingredient is magnetic fields. We need to know how magnetic fields are distributed in the universe, and that's tricky because we don't really understand magnetic fields at cosmological scales, and we don't really understand extragalactic magnetic fields. So this plot shows the volume filling factors of magnetic fields, and the volume filling factor essentially tells you what fraction of the universe, of the volume of the universe, is filled with magnetic fields larger than the value indicated here in the horizontal axis. So, for example, if we take this black line, for 10 to the minus 11, this volume filling fraction would be 0.5, 0.6, meaning that 6% of the universe would be filled with magnetic fields larger than 10 to the minus 11. And these here are different models obtained from cosmological simulations of structure formation that predicts the distribution of magnetic fields, both the large-scale structure of the universe, like galaxies, like clusters and filaments, and also in the cosmic voids. Speaking of these structures, the clusters, they have strong magnetic fields, clusters of galaxies, and they fill a very small fraction of the total volume of the universe, less than 1%. But usually people say that it's less than 0.1% general. This is just the uncertainty band, approximately. And here we have the filaments, which fill something between 20 and 0.1% of the volume of the universe and has a magnetic field slightly weaker than the magnetic fields in clusters. And here we have the cosmic voids, which is really something that we don't know about. There are some limits, as I'm going to discuss towards the second part of the talk, but it's very uncertain. The only thing that we can tell that it's not controversial about these magnetic fields in the voids is that they are less than 1 nanogauss, or 10 to the minus 9 gauss here. And they fill most of the volume of the universe. So if we are to understand the propagation of cosmic rays in the universe, probably this is one of the most relevant ingredients for statistical studies, because it fills more than 20% of the volume of the universe in total. Okay, and these are the interactions of relevant for cosmic rays propagation. So we have a proton with a background photon field. It produces gamma rays and neutrinos. these are the cosmogenic particles that I alluded to in the beginning. So a proton plus a CMB photon usually produces a pi zero that decays into gamma rays, or a pi plus, which decays into neutrinos. These are the cosmogenic particles, but we also have other channels of production of these cosmogenic particles, for example, through nuclear decay or through nucleus interactions, but this is not relevant at cosmological scales in general because the density of matter is very low. And this Bethe-Heitler pair production also produces these electron positron pairs as well, and so on. And the mean free paths for those processes that I mentioned before, so we have the photopion production. You can see here, it's shown as the dot dashed line. It's this line here, for example, in the case of the red protons. And we also have pair production, which is just these dotted lines. You can see that it starts to dominate at lower energies with respect to the photon pion production, in the case of protons, photo disintegration in the case of nuclei, as you can see here as this blue dashed line. And the adiabatic losses due to the expansion of the universe are shown here as a solid line at the top. And you have to combine all these ingredients to do the modeling of ultra-high energy cosmic ray propagation. But one of the things that is important to draw your attention to is the fact that, let's take this proton line, for example, you see that it starts to fall down roughly kind of sharply after 4 times 10 to the 19 electron volts. This is a consequence of this process, which is essentially the Gdk cutoff. And it essentially tells us the distance. For example, if you look at 10 to the 20 electron volts, if we see a cosmic ray with 10 to the 20 electron volts, it probably came, and if it's a helium, it probably came from less than 10 megaparsec. If it's nitrogen, it probably came from less than 30 megaparsec or so. Okay, so there are these interaction horizons. They exist for ultra-high energy cosmic rays, and they determine how far we can see in cosmic rays. And to study the propagation of cosmic rays, we developed this code, this framework for particle propagation, which is CRTOPA, which started as a cosmic ray propagation code, but nowadays we are working on the new version, which is much more general. It can be used for the propagation of high and ultra-high energy particles of various types, like gamma rays, for example, in the source, outside the source, in the intergalactic space. And this new version is coming out very soon. So among the capabilities of CRTOPA, it's very flexible. You just have to assemble the modules that are shown here as these bubbles. And for example, we have modules for several types of interactions. For example, electrons, they can undergo inverse Compton scattering, triplet pair production. And the physics for these particular interactions, here in the case of cosmic rays, all these ones, and these ones for photons, the physics for this is all implemented in the code nowadays. We can also do the propagation, use different types of propagation modes, a simple one-dimensional simulation if you're not really interested in arrival directions or arrival times. There is also this feature since a couple of years ago, which allows us to do an ensembled average propagation of cosmic rays. It started as a galactic feature, but it can now be used also in extragalactic space. So if cosmic rays are of lower energy, they diffuse a lot and it's hard to track them individually. So this treatment is an average over all possible particles. So it's slightly more efficient than our previous approach. There is also this is our usual, our former integrator for propagation, but there is also this new one that is going to be released with the new version of CRTOPA, which is faster than the usual Runge-Kutta method. And we also have several types of magnetic fields that can interface with magnetic fields coming from cosmological simulations. We have turbulent magnetic fields, dipolar, helical magnetic fields, and several types of galactic magnetic fields as well. This is all implemented in the code, and you can just assemble the simulation that you wish to run based on these modules that are already pre-implemented. And now moving on from CRTOPA, when we talk about the propagation of particles, there are some uncertainties that are relevant. In the case of ultra-high energy cosmic rays in particular, one of the factors is the EBL models. So the extragalactic background light, it's some radiation field that permeates the universe like the CMB, but it's different in terms of spectral properties. But it's relevant, especially for the propagation of ultra-high energy nuclei. And as you can see here, if you take two different EBL models, and if you plot one minus the other, the spectrum, you simulate the propagation through intergalactic space for these two different EBL models. You take the relative difference between these two, the spectra obtained with these two EBL models. This is what we see in this line. And as you can see, the discrepancy due to the EBL model, it's much larger than the statistical uncertainties of, for example, the Pierre-Roger Observatory. So really the EBL models, the uncertainties in the EBL models can affect the way in which you interpret the data measured, for example, by the Pierre-Roger Observatory. It also, here I illustrate for the case of the spectrum, and here for the case of the average composition arriving at Earth, because this example is for iron. The iron will photodisintegrate in intergalactic space during propagation. And if, again, we take the relative difference between these two EBL models, you can see that there is some uncertainty. And these uncertainties, they actually propagate also to the secondary particles that are produced via ultra-high energy cosmic ray interactions, namely the cosmogenic neutrinos, cosmogenic electrons, and cosmogenic photons. As you can see here, the discrepancies can be of the order of 30% or so. Another important factor is the photodisintegration. So the photodisintegration is essentially you have an atomic nucleus interacting with a photon and it produces something else. Sometimes it just loses a proton or a neutron or an alpha particle or whatever. But this is an important ingredient for the propagation of ultra-high energy cosmic rays. The problem is that the photodisintegration is not really that well understood. There are very few measurements in the lab of the cross sections for these processes. Therefore, there are some models for photodisintegration. And these models, for example, here in these plots, we show two, this PSB and these Thales models. And again, by playing the same game from the previous slide, the same kind of figure, you can see that the uncertainties in photodisintegration, photonuclear cross-sections, it leads to discrepancies in the spectrum that are much larger than the uncertainties of the observational uncertainties that you would get, for example, with the Pierre-Roger Observatory. It can be of up to like almost 50% or so. And these uncertainties, they also propagate to secondary particles, as you can see here. But in this case, these uncertainties are slightly lower than in the case of the EBL, the case of cosmogenic particles. And now that we understand more or less how ultra-high energy cosmic rays propagate in the universe, the most relevant processes, we can actually look for the sources of ultra-high energy cosmic rays. So look for the sources of ultra-high energy cosmic rays. If we were actual hardcore traditional astronomers, we would just look with a telescope to a given position of the sky. Can we actually do the same with cosmic rays? It's tricky because cosmic rays are charged particles. Therefore, they are deflected by magnetic fields. And because they are deflected by magnetic fields, we cannot really do ultra-high energy cosmic ray astronomy that easily, unless we understand magnetic fields. So going back to that plot that shows several models for the extragalactic magnetic field, as you can see, these different models, they give very, very different results. As you here, for example, compare this red line with this brown line. This is several orders of magnitude discrepancy, and it will obviously lead to very different results in cosmic ray propagation. In this case, because magnetic fields are more, the weight of the magnetic fields of the stronger magnetic fields is higher here compared to this red case. Of course, here we expect the deflections of cosmic rays to be larger than in this other case. And here it's even possible that the direction, the arrival directions of the cosmic rays will not correlate with the source that we are trying to correlate it with for maybe 10 degrees or so because of all these uncertainties. And then it starts to become a tricky business to do ultra-high energy cosmic ray astronomy, because we need to understand magnetic fields, but we don't really understand magnetic fields. But we can ask ourselves, okay, given that we know nothing about extragalactic magnetic fields, we can try to set some limits. So if we look at the orange curves here, we know the strongest magnetic field theoretically allowed. So the most pessimistic case, or optimistic, depending on your point of view here, it's more pessimistic for people working on ultra-high energy cosmic rays. So, if we want to study the most pessimistic case, we just have to set to study the case in which the universe is highly magnetized, such that the cosmic voids have the upper limits magnetic field strengths. This is shown through these orange lines. Each one of the orange lines is a different power spectrum for the magnetic field. And then we can play this game. Okay, let's study this upper limit case and see if we can do some kind of cosmic ray astronomy. And for that, we use these cosmological simulations, but I think I'm taking quite a long time during this talk, so maybe I can just skip the video. The relevant part is just that these points are the clusters of galaxies. You see that they are connected to filaments, and the black empty regions are the cosmic voids. And as you can see, cosmic voids, they fill most of the volume of the universe. And here it's just a 2D plot of the video that you've seen before. And trying to answer the question about the prospects of ultra-high energy cosmic ray astronomy. The average deflection of ultra-high energy cosmic rays in those different upper limit magnetic field models is shown here. So the average value shown through the line. This is the variance shown as a band, as a colored band around. This is assuming that the sources are uniformly distributed throughout the universe. And then we inject cosmic rays from all the sources, we collect them at Earth, and this is the average value that we get for the cosmic ray deflection. This is a simulation. We know where the source is because we simulated the source position. And then we can just look at the nearby sources, less than 10 megaparsec away, or between 10 and 20 megaparsec. And by comparing these three plots, what we see here is that it is still possible to identify nearby sources. And here, if the cosmic rays, they are very energetic, like 10 to the 20, deflections are less than 10 degrees. And less than 10 degrees.
Did we lose Rafael? Marcus, can you hear Rafael?
I can hear you, but I cannot. He's back on, Rafael?
No, I cannot hear Rafael neither.
Yeah.
Can you hear me now?
Yes.
You're back now.
Okay, I'm sorry. Yeah, let me just check.
Yeah, now you're good.
Okay, good. So, sorry. Just continuing here. So it is still possible to identify the sources, nearby sources of cosmic rays in this case. Here, if they are very energetic, here, if they are not so energetic. And as you can see, the deflection we are talking about in this case is like 10 degrees. 10 degrees for the ultra-high energy cosmic ray community. It's essentially astronomy. But if you look at a patch of 10 degrees in the sky, 10 degrees radius, that's not really astronomy because there are many sources there. But for the ultra-high energy cosmic ray community, that's as close as we can get to astronomy, unfortunately. But that's already something, an improvement. That's why it's not impossible to do astronomy in this worst case scenario, but we can use multiple messengers to really pinpoint the sources of the ultra-high energy cosmic rays. And now we start studying the cosmogenic neutrinos and photons. And going back to that plot that I've shown in the beginning. So as you can see, the flux of PV gamma rays, PV neutrinos, and EV cosmic rays, it's more or less as I've drawn the horizontal line before, right? And then we can ask ourselves, is there a cosmogenic connection or not? So is this flux related to this flux through a cosmogenic production process through ultra-high energy cosmic ray interactions? That's a reasonable question to ask. And let's try to answer this first. The Pierre Roger Observatory has been collecting data for quite some time, and we recently published a very detailed measurement of the ultra-high-energy cosmic ray spectrum, and there is also these measurements of the composition. Actually, this is the X-max, which is the depth of the shower in the atmosphere, which is a proxy for the composition of the cosmic ray. These measurements are available nowadays thanks to the Pierre Roget Observatory, the telescope array, and so on. And we can try actually to interpret both the composition and the spectrum within a single framework. We can perform a combined spectrum composition fit, and we can compare the observations at Earth with some theoretical models that we have, so some properties at the source. And that's what we did in this work here. We tried to fit the ultra-high-energy cosmic ray spectrum and the composition. We did this within a very simple scenario in one dimension, neglecting magnetic fields, and so on. And what we observe here is that if we try to do this fit under the assumptions that we adopted, which is one-dimensional simulation, sources are evolving with 1 plus the redshift to the power m, that's this m here, assuming that the sources have a power law spectrum with a given index alpha and a cutoff at an energy equal to R max times the atomic times the charge of the cosmic ray. In this case, our conclusion is that this type of fit favors a negative source evolution, meaning that the sources that are closer to Earth are contributing more to the ultra-high-energy cosmic ray flux than the sources that are more distant to Earth, with a relatively hard injection spectrum, so alpha equals to 1, roughly speaking, whereas, for example, for the typical Fermi acceleration mechanism, this value would be 2. And the spectrum is dominated by CNO, carbon, nitrogen, oxygen nuclei. And if we propagate those cosmic rays, if we calculate the cosmogenic neutrinos and photons, this is what we get. Let's start with the neutrinos. So considering the, let's take the 99% confidence level band shown here in orange. So the current detectors at this energy, the operating ones like Auger, it's 3 orders of magnitude above this cosmogenic neutrino flux. So it's really hard to detect the cosmogenic neutrinos. This will be a challenge for the next generation of experiments like GRAND. So GRAND, for example, 10 years of observations, which is this horizontal blue line, it might be able to probe at least part of this parameter space here of cosmogenic neutrinos. So we cannot really tell a lot about ultra-high-energy cosmic ray sources from the cosmogenic neutrinos. Then we can try to do the same with photons. With photons, it might be possible, but this band, it extends like down to 10 to the minus 13 or so. I didn't even plot it. So maybe if the parameter space is such that we are in this region, we might be able to probe ultra-high-energy cosmic rays using the diffuse gamma ray background. But it's still tricky. So the conclusion is that assuming we try to fit the ultra-high-energy cosmic ray data, and we just calculated from that what's the diffuse neutrino and photon flux that we expected. And the ultra-high-energy cosmic ray data does not seem to explain these ice cube neutrinos, nor these nor all of these Fermi measurements at the higher energies, at least. And going back to this plot, so there is this connection. Is there a cosmogenic connection? Based on the previous result, it's not clear if this cosmogenic connection exists. However, we can also ask ourselves, is there a source connection, meaning that the cosmic rays produce the neutrinos and the gamma rays that we observe? And I'm going through these 3 slides, and then I'll stop for to take questions. And then, yeah, because my time is probably running out. Okay. So yeah, the question is there a source connection? And I'm going to study here just one case of a recent work in which we studied the production of neutrinos from clusters of galaxies. We again used cosmological simulations of structure formation, and the clusters of galaxies are these dots. If you look at one cluster individually, it's shown here in the bottom panels, and you can see that these clusters, they are nearly spherically symmetric. To first order, it's okay, but if we go really want to do more detailed analysis, this starts to become asymmetric, and the asymmetry is because there are filaments connecting clusters and so on. But we use this kind of analysis, clusters of different masses sampled from this cosmological volume of 130 megaparsec cubed. And we propagated cosmic rays in individual clusters. Here is a cluster. This is the magnetic field strength. And as you can see, higher energy cosmic rays, they can kind of escape this cluster. But the lower energy ones, they are confined close to the cluster region before they can escape. So they diffuse here inside for a longer time. And if these cosmic rays, they interact with the cluster material, the photons and the gas in the cluster, producing neutrinos and photons. So we can now calculate the neutrinos that are produced via this process, the cosmic rays interacting in the cluster. And as you can see, if we take a cluster of mass 10 to the 15 solar masses, for example, we have a much higher neutrino flux than a cluster of 10 to the 13 solar masses. This is the first point I'd like to make. This is for an individual cluster of this mass. If we now calculate the diffuse neutrino flux due to all the clusters in the universe, of course, it depends on the properties of the cosmic rays that we are talking about. So the cosmic ray spectrum, where the spectrum cuts off, which is Emax, and the spectral index. But we can estimate the diffuse neutrino flux. It's shown in this brown reddish line here for particular scenarios, okay? From all clusters in the universe, and these clusters were sampled from cosmological simulations. If we consider this particular spectrum, injection spectrum for the cosmic rays, we get that the ice cube flux at this 3 times 10 to the 14, so 0.3 PeV, it's overshot by the neutrino flux that we obtain from galaxy clusters. But if we consider the alpha equals 2, so the spectrum index for the cosmic rays is slightly higher, then this flux is not overshot by the diffuse neutrinos from clusters. And with this, I finished the first part. I'll go very quickly over the second part in 5 minutes because I spoke a lot already, but it's a good time to take questions, I think.
I think Marcus has a question.
Yeah, I have a quick question. So you made this comment that so you compared the cosmogenic gamma rays to the cosmogenic neutrinos, and you said that we might be able to measure the cosmogenic gamma ray part. But my question would be, how would you be able to distinguish this part from other gamma ray backgrounds? Do you have any idea?
That requires knowledge of the other backgrounds. That's very tricky. Yeah. It requires knowledge of other backgrounds. For example, we know that blazars are the most relevant components there, but there might also be some components due to dark matter annihilation. And dark matter, if you just change from one model to another, you can get a factor 10 or 100. So it's very difficult.
Yes. Okay. Thanks.
So I have one question that I've asked you before, Rafa, is how much does the uncertainty in the magnetic fields, extragalactic magnetic fields, affect the neutrino flux in terms of how high it can get or how low it can go?
Yes, I have an additional, I didn't prepare an additional slide on that, but there is a work by Witkowski and Kampert. I can send you the reference probably later, but the flux increases by slightly less than 1 order of magnitude if you consider extragalactic magnetic fields, but they considered only one model. My guess, my intuition tells me that if you consider the stronger magnetic field models, this flux will increase a lot, like by maybe 2 or 3 orders of magnitude even.
We still have the upper limit from ice cube, so it cannot be larger than that. But there's, I think you're right. There's like 2 or 3 orders of magnitude between the prediction and the upper limit. So okay.
Exactly. Yeah.
That's encouraging. Yeah.
Yeah, but it's computationally very difficult to do this kind of study. It has been on my to-do list for a while, as we've discussed this before, but yeah.
Yeah. All right, do we have any pressing question? I have one maybe final question before you move on. You were showing in your slide 30 that you were doing the fit of the high energy cosmic rays to the Auger data, so the data points on the left and on the right. But on the right, you also show the TA points. And I'm curious because this is always shown in terms of fit to the Auger data. But what happens if you actually include the TA data as well?
Yeah, I don't really know. It's something that when this work was being done, I also asked myself if we do a global fit. But then I think the fact that TA and Auger are in different hemispheres will start to play a role, and we would need to move to a 3D simulation. Because southern sources, for example, we see in the south with Auger, we see Sene very bright, but in the north, it's not the same.
That's a good point. You also need to account probably for the energy uncertainty of each one of them. And we know that they are compatible when you run one through the machinery of the other. So I guess that needs to be taken into account somehow. Because if you don't do that, they actually seem very, very different.
Exactly, yeah. But also the results of this fit, it's also subject to uncertainties like in the EBL model and so on. And there are so many uncertainties that, to be honest, I shouldn't be saying this, but this kind of fit cannot really be trusted as a fit. It can be trusted to give you an intuition of how things behave only.
No, I agree with that statement, yeah. All right, any other question? I don't see any, so yep, please go on.
Yeah, can I have 5 minutes?
Yeah. Go for it.
So this second part is about gamma rays. And again, going back to this part, we were talking about cosmogenic particles. But if the cosmogenic neutrinos and the cosmogenic photons have the same origin, and they are produced through the same process, photon pion production, they are produced with the same energy. But then why am I talking about cosmogenic photons in the TeV energy range? The answer to this is that there is intergalactic propagation. So gamma rays also propagate in the universe. Going back to that picture, we have low energy photons that they just travel essentially in a straight line, but high energy gamma rays, they also travel in a straight line. However, they can interact with the EBL and the CMB during their journey. And this interaction produces electron-positron pairs, which are affected by these intervening magnetic fields outside our galaxy. And these electrons and positrons, they upscatter CMB photons then and produce gamma rays. And these gamma rays may actually be these ones and produce more pairs. That's why this is called an electromagnetic cascade process. The opening angle of these electrons and positrons, it depends on the magnetic fields, for example, and so on. Therefore, high energy gamma rays, they do travel in a straight line, but they interact. And the interaction produces charged particles, and the charged particles are deflected by magnetic fields. So it's slightly tricky. The processes that are relevant for gamma ray propagation are mostly pair production, double pair production, so electron-positron, 2 electrons positrons, inverse Compton scattering, and a triplet pair production, which is wrong in this equation. I'm missing a E minus E plus pair. I'm sorry. Yeah. This is just the higher order inverse Compton scattering process. So we'll just add 1 pair to this side. And the mean free paths for these processes, they are shown here, but I'll just skip because I don't have a lot of time. But bottom line is that the pair production, which is relevant for the high energy gamma rays, especially you're talking about at TeV or 10 TeV energies. The EBL is the dominant background, and the CMB is the dominant background for inverse Compton scattering. That's just the bottom line, and something that you should know. And how to constrain intergalactic magnetic fields with gamma rays, because I mentioned that the electron-positron opening angle of the pair, it's sensitive to the intervening magnetic field. Then we can try to use that information to constrain magnetic fields in the universe. But we don't really know how magnetic fields originated in the universe. We don't know their properties. And let me just make a definition here first. Intergalactic magnetic fields, IGMF. So intergalactic magnetic fields are the ones in cosmic voids. Okay, I'm not talking about magnetic fields in clusters or filaments, just in the voids, because the voids fill most of the volume of the universe. And these magnetic fields are particularly interesting to understand how magnetic fields originated, because they are kind of, they remain virtually unaltered over the cosmological evolution of the universe. They are just there. They are, the seed magnetic field from the early universe just remains there in the center of voids, undisturbed by whatever is happening around. And there aren't many limits on these magnetic fields. So the two relevant observables is the magnetic field strength and the coherence length of this magnetic field. So the scale at which these magnetic fields completely lose track of the direction that it had in the previous cell. We know that the coherence length should be less than the size of the universe, and it should be larger than this value, otherwise the universe would be a giant resistor. We have some constraints on the magnetic field strength from Zeeman effect and from CMB measurements as well. And there are theoretical arguments that excludes this teal region due to MHD turbulence decay. And the interesting one is this purple region. The purple region shows the lower limits on the intergalactic magnetic fields due to electromagnetic cascades initiated by gamma rays. This has been questioned at some point, but I don't think I'll have time for that. But there are essentially three strategies that we need to, we can adopt to study these intergalactic magnetic fields with gamma rays. So we have to remember that the gamma rays, they will pair-produce the electrons and positrons. They will first photon scatter CMB photons mostly. And now we are talking about the lower energy regime here, because we are aiming at constraining the magnetic fields in the universe. Therefore, there are three strategies. The first one is point-like sources will appear extended, as can be seen here. So magnetic fields tend to the -16 Gauss, -15, -14. And as we increase the magnetic field, these are the number of gamma rays arriving. And you can see that this halo starts to form around the point-like source. In this case, it's this blazer, 1ES0229 + 200. The second one, the second strategy, only works if the object is flaring, a bursting source, which is just to look at the arrival times of the gamma rays. And the third one is just a combination of strategies 1 and 2, essentially leads to spectral changes, as seen here. So magnetic fields, weak magnetic fields essentially lead to this flat behavior. As the magnetic field starts to get stronger, the curves start to go down. And naively, this result, although it's not a fit, you can already say something. If you trust the assumptions for this simulation, magnetic fields should likely be somewhere in between the red and the orange lines. So 10 to the minus, something between 10 to the -15 and 10 to the -14. That's the strategy. And
wait, Rafael, can I ask a question about this plot?
Yep.
So if you're saying that the gamma rays will cascade down, why are you not seeing a pileup of low energy gamma rays in these curves as you crank up the magnetic field?
Exactly. That's a very good question. The point is that as they cascade down and this halo starts to form, the gamma rays, they will start to go to be, they are not contained within the point spread function of your detector. So essentially this measurement, it has to take into account the point spread function of your detector, because if you take the whole sky and if you integrate, of course, the curves, the total integrated flux will be the same. Yeah. But if so you take into account the point spread function, you cannot.
I see. You're just missing them. Okay. Yeah, thanks.
And also some of them will arrive many years after. And all this is relevant because we, as I said, we don't know anything about magnetic fields, which is something interesting on its own, but it's also useful to have better models of magnetic fields for cosmic ray studies. So this is where everything starts to come together. And in the last 2 minutes, I'll just present multi-messenger methods that we developed to constrain intergalactic magnetic fields using both neutrino and gamma ray observations. As you know, in 2017, there was this IC 170922 neutrino event that was observed by IceCube. It was observed in correlation with electromagnetic radiation across all spectrum. Here you can see the observations by the MAGIC in gamma rays. Here it's by Fermi-Lat, also in gamma rays, but at slightly lower energies. And this flare lasted for about 6 months. The neutrino flare lasted for about 6 months, roughly speaking. And we can use this type of information, the neutrino flare lasted for 6 months. And we can use the observations that we have in gamma rays through MAGIC and Fermi-Lat, for example. And we can do a combined fit of this object. So essentially the activity of this blazar, we can fit it, the Fermi-Lat data, the MAGIC data, assuming the neutrino information of 6 months duration. And we can, from that, extract we can constrain magnetic fields, intergalactic magnetic fields. So this method, it's not very constraining. We used CR-Propa simulations. We have to consider that the object might be flaring in neutrinos for some times, like 6 months, and then it's quiescent. And then there is the 6 months high state wherein it's active. And then we have to combine these two components to see what the flux that we would get on Earth. And that's how we get these constraints here. Okay. I won't go too much into detail, but the bottom line is that we can get like some constraint on intergalactic magnetic fields. But interestingly, this is the first constraint the coherence length of intergalactic magnetic fields was using this method. Of course, if you trust the neutrino gamma ray correlation. This has been a question nowadays, as you probably know. If you trust this correlation, we can get a handle, we can constrain the coherence length and magnetic fields together. And based on that, I'll just skip to my conclusion because I don't have more time, and I'll take questions.
Thank you very much, Rafa. Are there any questions? I have one question on something you just said. Actually, it made me think. So you were showing that one, yeah. So that comes from the multimessenger observation of the TXS blazar. Have you thought about doing this also for the alleged tidal disruption event coincidence detection?
Yes, I did. I'm starting to set up the simulations now. Yeah.
Right.
But the significance is lower for that one.
That's true, but the environment is very different, right?
Yeah.
So the flaring state might is months instead of well, okay, it's also months. No, that doesn't change.
Also.
Yeah, you're right. And I think Marcus has some questions.
Yeah, I have. Sorry, I could not quite follow your argument here. I have to admit. So you're saying that, I mean, does the neutrino have any influence on this result here, or are you comparing gamma rays at different energies?
No, this is essentially a fit to the gamma ray measurements at different energies. The neutrino only tells us one thing, the duration of the flare, because this is a two-component model. If you look here, there are these parameters. So there is, I'm assuming that the source is a power law with an exponential cutoff at a given maximum energy, and that TXS was kind of quiescent during this low state, L, and there was also the high state. The high state, it's the neutrino flaring period. That's where the neutrino information comes in.
So when you say here, CR-Propa simulation, you are referring to, are you referring to the cosmic rays, or are you referring to the electromagnetic cascades here? Or?
To the cascades only, yeah, cascades. Because as I mentioned now, CR-Propa, it's not more only cosmic rays, it can do almost everything. So.
Yeah, and but how can you guarantee that photons that we observe have some connection to, sorry?
You cannot actually. The assumption is neutrinos came out, but the photons might not come out. The source might be opaque to gamma rays. But if you assume if you assume that gamma rays come out, then that's the result you get. And some gamma rays do have to come out because we have to get, I think I have a backup slide here. So this is a phenomenological model. So the injected spectrum can be seen as a superposition of the low state and the high state with this eta parameter. And there is a cascade contribution because we see, but the spectrum is here, yeah. Because we see these points, we can try to fit these points. And these points necessarily imply that the result of the fit come out. And the result of the fit is that there is at least TV gamma rays coming out of this object.
So the magnetic field that you are trying to constrain here, is that, I mean, on what scales are we looking for this? Is this the void, the field in the void, or in the vicinity of the source?
It's the field in the void, because that's where the gamma rays will interact and produce the electron-positron pairs. So it's a magnetic field in the voids, and we scan most of the parameter space in coherence length. So it's not for a fixed coherence length like most people do. This is a combined, this is a joint magnetic field and coherence length constraint.
Oh, interesting.
So maybe to Marcus's point, is there any contribution coming from the magnetic field of the source itself? Kind of like when you see the dispersion measure of a FRB, there's some part that comes from the source and some part from the propagation.
I didn't actually do that analysis because it's a blazer, so the jet extends for quite some distance. But my guess is that the gamma rays, in order to interact, if they escape the object, they will essentially be already in the intergalactic medium, and the mean free path for pair production, it's of the order of hundreds of megaparsec, or at least tens of megaparsec. So it will definitely not be close to the blazer anymore.
Yeah. All right. Are there any more questions? I don't see any hands. I think, Marcus, you just unmuted yourself. Yeah.
I have one last question, and then I have to leave for another telecom. But at the beginning, you talked about these, you made a comparison between systematic uncertainties of these cosmic ray interactions in radiation backgrounds and the statistical uncertainty. I was wondering, you have also, yeah, exactly this one here. I was wondering, you also have sometimes the case where you start with a very heavy nucleus, and then you have these cascades, which are basically then interacting again and again and again. So I was wondering, the systematic uncertainty that you show here, is this assuming that you have one interaction and then you compare to the systematic, or that you have actually a cascade of these?
You have a cascade. I didn't go into details here because I didn't have time, but this was just a one-dimensional setup with only nitrogen in this example, and this nitrogen and we collect everything at Earth as it would be in the real case. So it's the cascade.
This cascade. Okay, thank you.
So then, for closing, actually, let me ask one question. On your slide 45, you show this electromagnetic lower limits on B coming from the electromagnetic cascades, and I was thinking, how do you actually get that? Because how can this be a lower limit? You can always have a degeneracy between how much the cascades develop on a magnetic field or how much the sources are injecting, right?
Yes, that's true. The argument that it's a lower limit is the following. We know the point spread function of the detector. So we expect to have, that relates to the question that you asked before about this upper right plot. So you have to measure to look for halos. So you have to look for a significant flux within the point spread function that allows you. So the non-observation of these halos here, it implies a lower limit, because if there is no magnetic field, then everything is contained within the point spread function of your detector, in the absence of magnetic fields. But if you include magnetic fields, it starts to spread out.
Yeah.
Yeah, that's why it's a lower limit.
Okay, I see your point. Otherwise, you would see like a point
Exactly.
like thing. Yeah. Okay.
Yeah.
I get it. All right. Thank you very much, Rafa. I'm sorry that we couldn't have you here, but I hope we can have you here in the future. Everybody else, thank you very much for joining as usual. We'll see each other in a couple of weeks. And Rafa, I'm gonna send you a couple of emails because you just gave me a couple of ideas.
Okay.
All right. Thanks, everybody. Bye-bye.
Bye.